All right, it's 9:40. Let's get started. Last week, huh? I hope it's last week. What a long semester. Anyway, quiz 13's out. There should be an entry in Blackboard that shows what your quiz score is minus the lowest 3 grades. So you should be able to see that. Homework 5 solutions I posted this morning. That was a hard one. So if you did any of homework 5, take a look at it. And as you probably all know, I'm doing the final exam review class tomorrow. Okay? Any questions before we start? Okay, so what did we talk about last week? Undecidability, yeah. That's the thing we talked about. So we showed that some languages were not decidable. So what was an example of a language that we showed wasn't decidable? Yeah, ATM was one. So ATM, and that is all pairs of machines and strings. So M is a M, and W is in the language of M. Yep, so that's the language we talked about in class. We showed that that was undecidable because if it were decidable, then we made another Turing machine that disagreed with itself. Okay, with whatever it said, it did the opposite. So therefore, we showed that ATM was undecidable then. What was another language we saw was undecidable? ETM, yeah. So we had ETM, and that's about asking emptiness. So it's just a single, just a bunch of single machines, only machines, and M is TM with empty language. Yep. So that's ETM. And how did we show that ETM was undecidable? Right, so if I could decide ETM, then I could make a decider for ATM, but that can't exist. So there's no way that ETM could have been decidable. Okay? What was that process called where we assumed a decider for this and made a decider for something that was undecidable? What did we call it? A reduction, yeah. So there was a reduction from ATM to ETM. And we wrote that as ATM less than or equal to ATM. We reduced ATM to ATM. So if we could decide ETM, then we could decide ATM. All right, yeah.
Sorry, could you just repeat one more time how we figured out ATM was undecidable?
Because if it were decidable, then we made this machine D that we used this supposed decider, and if we fed D its own description, then it disagreed with itself. So it would say, I accept my own description if and only if I reject my own description. But that can't possibly happen. So therefore, the only way it could have made that machine was if ATM was decidable. But that can't happen, so therefore it can't be decidable. Okay? Any questions about these? What is something else we did along the lines of undecidability? How did we get many more languages undecidable? Some theorem that really makes me hungry. Rice's theorem. Yep. That has some humor, right? All right. So Rice's theorem. Well, what did that say? What did Rice's theorem say? Okay, so something along that line. So every non-trivial Well, what is the thing that's non-trivial here? Property, okay. So, but property of what? Of the language, yes. So, of the language, but language of what? Of Turing, it's got to be Turing machines, so language of TM, but just Turing machines, or some other qualification? Does a language have Turing machines in it? No, what does it have? It has Turing machine, it starts with a DE. Descriptions, right? So TM descriptions. You got the first two letters, right? Yeah. So, like, ETM has Turing machine descriptions in it. So, what does it mean to be a property of the language of Turing machine descriptions? Ignore non-trivial for a second. What does it mean to be a property of the language? Well, what we found is that if you have two arbitrary Turing machines with the same language, should anything other than the language decide whether they belong to the property or not? No, it has to be a property of the language. So if you have two arbitrary Turing machines with the same language, then that must mean either both have the property or neither do, because they have the same language. So therefore, it can't ever be the case that one has the property and one doesn't. And we'll see how to do that in a second. All right, well, what does that word non-trivial mean in this context? Okay. Right, so that must mean that there is some Turing machine that has the property and one that doesn't. All right. Using and so what about these properties does Rice's theorem say? It's undecidable. No. Everyone is undecidable. So that's a handy tool. So can I use Rice's theorem to prove ETM undecidable? So we're going to be doing a series of checks each time. Does this language ETM consist entirely of Turing machine descriptions? Yeah, so that's easy to check. Is it a property of the language of Turing machine descriptions? Yeah, so if I have two Turing machines with the same language, either they're both empty or they're both not empty because they're the same language. So they either both are in ETM or neither are. So that's good. What about non-trivial? Yeah, so have the machine that rejects everything, that's in there, and then the machine that accepts everything, that's not in there. So therefore, it's a non-trivial property. And by Rice's theorem, ETM is undecidable. Okay? Can I use Rice's theorem to prove ATM undecidable? Well, let's check. Does it consist entirely of Turing machine descriptions? Sure. It's got that input on there. Does it consist only of single Turing machine descriptions? No, it has this input right here. So therefore, I can't apply Rice's theorem to prove ATM undecidable. Okay? What about this other language that we saw, which was EQTM, which was pairs of machines? And then the condition is not that important. But can I use Rice's theorem to prove EQTM undecidable? Well, let's check. Does it consist entirely of single Turing machine descriptions? No. So therefore, I can't use Rice's theorem to prove that undecidable. Okay? But I can use it for ETM because it's a non-trivial property of the language of Turing machine descriptions, and you only have one Turing machine. Any questions about these? All right, so let's see. And one more thing. Behind the scenes of how we proved Rice's theorem, how did we prove Rice's theorem? What happened behind the curve? Well, we must have done some type of reduction. What did we reduce from and to? What's an easy language to prove, use a reduction from that we've used over and over? ATM. So the proof of this was reduction from ATM to the property. Okay, so so all it is reductions. Either doing it directly, a direct reduction, or using Rice's theorem. So I want to prove several languages undecidable. So like this first one. I want to check if a Turing machine's language is infinite. So we're going to do Rice's theorem and a direct reduction. So let's do Rice's theorem first because that's much easier to do. Well, can I apply Rice's theorem to this language? Well, let's check. Does it consist entirely of single Turing machine descriptions? Yeah, so that's an easy check. That doesn't mean I could apply it, it just means I can't guarantee I can apply it. All right, is it a property of the language of Turing machine descriptions? So if I have two machines with the same language, could it ever be the case that one of them is in infinite TM and the other one isn't? No, because since they're the same, either they're both infinite or they're both finite. So either both descriptions of the machines, so I'm going to abbreviate it to ITM because I don't want to write it over and over. Either they're both in infinite TM or they're both not in infinite TM. Okay? So it can't ever be the case that one of them is in and one of them's out. Okay? So I showed it's a property of the language of Turing machine descriptions. Now I need to show it's what? Not trivial. So what would I need to convince you, show you to convince you that this is a non-trivial property? Right, I need to give an example of a machine that is in there and an example of a machine that isn't in there. All right, so can you give me a machine that is in there? Yeah, how about a machine that accepts everything? Therefore, its language is infinite. So let M1 be a TM with that accepts everything. Therefore, the description of this machine must be an infinite TM because its language is everything and that is infinite. Can you give me an example of a machine that isn't in infinite TM? Yeah, rejects everything. Yeah. So let M2 be a TM that rejects everything. And then therefore we can see M2 is not in infinite TM. Okay? So I showed us a non-trivial property of the language of Turing machine descriptions. What can I conclude? It's undecidable. How do you know? By Rice's theorem. If I don't say the words by Rice's theorem or similar, then this means absolutely nothing. But I need to say I'm applying Rice's theorem here because I met the conditions of the theorem. So the most important words are by Rice's theorem. And then from that, we know that ITM, infinite TM, is undecidable. Okay? Any questions on how we did that? Okay, so let's do an actual reduction, direct reduction from some undecidable problem. Well, I have a choice. I can choose, say, ATM or ETM or similar. But which one do you think would be easiest here? Well, what does Rice's theorem use on the back end? ATM. So maybe we can do ATM. Because I know since we did Rice's theorem, ATM must work. Well, actually everything works, but ATM definitely works for sure. So let's reduce ATM to ITM. Okay? So what does that mean? That means if I could decide infinite TM, then I could decide ATM. So let's suppose I could decide ITM. So suppose D decides ITM. Okay? So now I gotta outline a decider for ATM. So what does a supposed decider for ATM take as input? What does ATM take as input?
Yeah.
Sorry? If I want to feed something to a decider for ATM, what do I have to give it? Yeah, I need to give a machine and an input, right? So I gotta give those two things. So on input MW, where M is ATM, and W a string. I better not say that W is in the language of M because I can't decide that. Well, let's see. I gotta use this decider D to my advantage somehow. So if I feed M to D, that will tell me whether M accepts infinitely many strings or not. But does that tell me whether M accepts W or not? No, it tells me nothing. It could accept every string but W, right? And it would be infinite in that case. So I need a better idea. So instead of feeding M, let's feed another machine that we're going to make. And what we want from this machine is that its behavior will be infinite or not, depending on whether M accepts W or not. So I'm going to make a machine M prime that takes arbitrary input and what do we want to do? We want, for example, you could do this a different way, but an easy way to think about it is, let's make M prime's language infinite if and only if M accepts W. Okay? So if M does not accept W, let's let M prime's language be finite. If it does accept W, we'll let it be infinite. What's your favorite infinite language? Sigma star, for example. What's your favorite finite language? Empty set. You could have picked any finite set. It doesn't actually matter here. As long as I have a finite set to work with and an infinite set to work with. Okay, let's see. So no matter what, I want to accept the finite language that we pick. Okay? And then if M accepts W, let's accept everything else. Okay? So by default, we'll have a finite language, and only if M accepts W, we'll accept everything, and therefore have infinite language. So I've already accepted the strings in the empty set, so I'm already done with that. So now I need to run M on W and then accept X if M accepts W. So run M on W. If M accepts W, then what we just said, we need to accept X as well. Is there something wrong with that? I said run M on W, but reasonably you can say that takes an infinite amount of time to do, right? Is that a problem here? What's that? Right, so I'm going to feed this to a decider which will always stop. No matter how this machine's built, it will always stop, supposedly. Okay, well, let's see. So does this get what we want? Well, if M accepts W, then that fact is always going to be true. It'll never not be true. So no matter what X I feed into M prime, it'll accept it anyway. So its language is everything, sigma star. If M does not accept W, well, could I ever get to this accept X down here? No. So what is the language of M prime if M does not accept W? It must be the empty set, right? Because there's no way to accept anything otherwise. So it's either empty set or sigma star, depending on behavior of M. So let's let D figure it out for me. So run D on description of M prime. And we know D must stop in a finite amount of time. So if D accepts M prime, otherwise if D rejects M prime, then we'll see what happens. Well, let's see. If D accepts M prime, that must mean M prime's language is infinite, right? Well, what's the only way that M prime's language could have been infinite? If I made it to this step, but the only way I could have made it to that step is if M accepts W. So therefore, I just determined M accepts W. What should I say to my supposed decider for ATM? I just determined M accepts W. And I'm trying to decide whether M accepts W. So what should I say to here then? I should say accept. Because I just determined M accepts W. If D rejects M prime, that says M prime's language is finite. Well, if it's not sigma star, it's empty set, because that's what we just determined. If it's empty set, then what does that mean? M could not have accepted W. So what should I say to my decider for ATM? Reject. And it's clear that all of this could have been done in a finite amount of time, given D. Okay? But I just made a decider for ATM, so what can I conclude? There's no way infinite TM could have been decidable. So infinite TM is undecidable. Okay? Any questions about that? Suppose I did this. I made this a very small change with having at least 5 states. Can I now apply Rice's theorem? No, because, well, it's still a non-trivial property because I could still find a machine that is in there and one that isn't. But can I show it's a property of the language anymore? No, because I can find a machine that I can find 2 machines where they have equal language. One of them, both of them have sigma star as their language. One has 6 states, one has 4 states. That's easily done. So I can't, so I found an example where one machine had the property and the other one didn't. Okay? So I can't apply Rice's theorem here. But can I do a reduction? Yes. So what I would do here is I would add an intermediate step to add states to M prime as necessary. So that's easily done. And D will do the exact same thing as we wanted because I guarantee it'll have at least 5 states. So that condition might as well not be there because M prime will always have at least 5 states. Okay? So I can always do a reduction, but I can't always do a application of Rice's theorem. Any questions about that? All right. So let's look at this one. So it's very similar. And what I want to check is whether the empty string, a specific string, is in the language of M. So we're only going to do a application of Rice's theorem here instead of a reduction because it turns out if you did a reduction, it's exactly the same as this. Word for word, exactly the same. Okay? So let's do Rice's theorem instead. If we could use Rice's theorem. So can I apply Rice's theorem? Well, let's check. Does it consist entirely of single Turing machine descriptions? Yeah, that's easy to check. Is it a property of the language of Turing machine descriptions? Well, let's check. If we have 2 machines with the same language, could it ever be the case that one contains the empty string and the other one doesn't? No, that's not possible. So we actually get the same conclusion as before. Exactly the same. Okay. Now what do I need to do? And I didn't show it's not trivial. So, examples of a machine that does have the empty string in its language and another one that doesn't. Same ones. Right? Same ones. So, same example. And therefore, by Rice's theorem, ESTM is undecidable. So it's funny, like the conclusion is almost as long as the proof, but it's really easy to apply Rice's theorem if you can apply Rice's theorem. Okay? But any questions about that? Okay, so I'm going to do one that was suggested in an earlier recitation on Monday, and it's not on the handout, but I think it's really cool because I said that the reduction for this one is exactly the same as the other one, but this reduction is going to actually be slightly different, which will make it interesting. I hope. So it's called sub-TM, and it's all pairs of machines. So M1, M2 are TMs, and the language of the first one is a subset of the language of the second. Okay? So we did sub-TFA before, but this is kind of like you have a system and a specification, and you want to check does the system satisfy the specification and does nothing else. Well, this is undecidable, unfortunately, in general. So can I apply Rice's theorem? No, why can't I? It has more than one termination. So I have to do a reduction if I want to show it's undecidable. But what language should I use? Well, I could use any one of them, but which one will be easiest? Is there a language that looks kind of like that we've shown was undecidable? EQDM. Instead of subset, it was equality. Okay, maybe let's try that. Let's try to reduce EQTM to subTM. So, like, it's now erased unfortunately, but like the reduction, we need to assume that subTM is decidable, and therefore, if it is, then EQTM is decidable. So suppose D decides subTM. Then now, with that, I gotta make a supposed decider for EQTM. So what is a supposed decider for EQTM take as input? It takes two term machines. Okay? So on input, the description of two term machines. So using D, I want to say yes if those two machines have the same language, and no if they don't have the same language. How can I use that subset thing to help me? Well, if you have two machines with the same language, what do you know about their languages in terms of containment? Well, if they're equal, each one contains the other. So could I run the supposed decider twice? Once for M1, M2, and then the other time for M2, M1? Could I do that? Yeah, if the answer at both times is yes, then that must mean that they contain each other, which means they're equal. If one of them says no, then they can't possibly be equal. So run D on M1, M2, then run D on M2, M1. If D accepts both times, we accept. Otherwise, we should reject because they're not the same language. Okay. So I don't like the now erase thing. I don't have to run a decider only once. So a supposed decider only once. I could repeatedly use the decider over and over and over, as many times as I like, as long as it's a finite number of times. Well, here we just decided EQTM, but it can't be decidable. So we must conclude that sub-TM is undecidable. Because if we could, then we could decide EQTM. Any questions about that one? Yeah.
So the way that we jump to the final conclusion is because we say that because we know that EQTM is undecidable, then we know that sub is therefore undecidable.
Yep.
So in a lot of tests, if we ever had to do a problem like this, we have to first prove EQTM is undecidable.
Well, we proved it in class, so.
But then, like, do we have to write that proof out, or?
Oh no. It's just cite the proof that we did. We showed in class that EQTM is undecidable, therefore sub-TM must be undecidable. Okay. Yep. There's no. Don't reinvent the wheel. Something we all know. But any other questions about this? So let's talk about that last one. How many of you know about CSE355? So it's the graduate version of the class, and this problem on here was actually a homework problem when I took it. So this actually is one of the problems from that class, and it's a very cool problem. So what we have is this function called L of m, and what is it? It's the length of all the strings in L of m. So, for example, if this machine accepts everything, then it has at least one string of every length. So L of m in that case would be 1 star, because it has one string at least of every length. Another example, if m rejects everything, then it contains no strings of any length, so L of m would be empty set in that case. And what we define is raglen Tn. And what is this? This is just a bunch of machines, and this is Tn. And the lengths, I call it the length set. The length set of m is regular. So like that machine that accepted everything, that machine that rejected everything, both of them are in there because sigma star and 1 star and empty set are both okay? Are both regular. So unfortunately, this is undecidable. Can I apply Rice's theorem? Let's check. Does it consist entirely of single Turing machine descriptions? Yep, easy check. What about non-trivial property? So if I want to show that it's a property of the language, if L of M1 equals L of M2, if I have two machines with the same language, could it ever be the case that one of them has regular length set and the other one has non-regular length set? They're the same language, so what do you know about their length set? They're both the same. So therefore, they're either both regular or both not regular. So, same conclusion. Well, actually, I should say that little l of m1 is equal to little l of m2. And then therefore, the conclusion easily follows. Could I find a machine that has that property, that does have regular length set? Yeah, I named two of them. So let M1 be a Tn with L of M1 equals everything. Therefore, little l of M1 is 1 star, and then therefore M1 is in regular. Okay. But now here's the hard one. Can I find a Turing machine that has non-regular lengths? And so there are many examples, but an easy one is, let's pick a non-regular unary language. So over one symbol. Do we know of a non-regular unary language? We actually showed two of them in recitations. Yeah, so primes. Yeah, so prime lengths. Yeah. So let M2 be a Tn with L of M2 being 0 to the P, where P is prime. We actually show that that's not even context-free, so it can't possibly be regular. So what is the length set of M2? Well, it's just 1 to the p, where p is prime. So, because it's nice to work over unary languages like this, because it's just a direct translation from zeros to ones. So, that must mean that M2 cannot possibly be in regular. Because its length set is non-regular. Okay. So for that reason, I just showed it's a property of the language of Turing machine descriptions, and then showed that it's a non-trivial property. So therefore, bi-res is 0. Raglan TM is undecidable. Okay. Any questions about that? Let's do a direct reduction. So, what language should we reduce from to Raglan TM? Any particular choice? Let's do ATM. So let's do ATM reduced to regular. So again, we're going to suppose D decides regular. Then we got to make a decider for ATM based on that. So on input MW, and then I don't care what that M is a Turing machine, W is strength. Well, if I feed M into D, and D says, okay, your length set is regular or not, does that tell me any information about whether M accepts W? No, it tells me nothing, right? So I got to make another machine, and then feed it to D. So, like for construct M prime, which takes arbitrary input X, and then now we gotta figure out how M prime is going to work. So what we could do is, or what we want really, is that we want M prime to have regular length set if and only if M accepts W. Okay? So if M accepts W, I want to have regular length set. What is a nice language that has regular length set? Sigma star, that's one of them. So like before, we'll accept everything. But if M does not accept W, I want it to have a non-regular length set. Do we know of a language with non-regular length set? Yeah, primes. Okay? So we gotta think about how we're gonna make this thing. So if M does not accept W, then whatever I accepted before, I want that to be the non-regular length set. Okay? And then if M accepts W, I'll accept everything else. And at that point, its language would be sigma star. Okay? So by default, I'm gonna accept the language that I want to get if I want to show it's not in regular TM. Okay? So by default, I'm gonna get the prime one, and then if M accepts W, I'm gonna get everything else as well. So what do I need to check about X? Immediately. I want to accept prime lengths no matter what. So what do I need to check about X? Sorry? What do I need to check about X? It better have prime length, right? If it doesn't have prime length, then I need to then check if M accepts W. So let's see. If X has prime length, accept X. Okay. So no matter what, the language of M prime is going to have the prime length strings, no matter what. Okay? But if M accepts W, what should I do? Well, if M accepts W, what do I want M prime's language to be? Just went over this. What do I want M prime's language to be if M accepts W? Yeah, I want it to be sigma star, right? So if it's not of prime length and M does accept W, what should I do with it? I better accept it. So, and then at this point in B, X does not have prime length. So run M on W. If M accepts W, accept X. Okay? So let's think about it. Let's recap. So what are the possibilities of M prime? Well, if M accepts W, I will accept the things that are of prime length and everything else, but that's sigma star. So what about the other case? If M does not accept W, I will never accept things of non-prime length. So therefore, the only things that it could have accepted are of prime length, but that has a non-regular length set. So I'm going to run this decider D on M prime. If D accepts M prime, and then the other case is D rejects it. Well, if D accepts M prime, then that must mean it has a regular length set. So, what do I know at that point then? If it does have a regular length set? Well, its language must be sigma star because it's either sigma star or prime lengths. So if it's sigma star, that must have meant M accepted W. So therefore, what should I say to my decider for ATM? I better accept it because I just determined M accept W. What should it say? If D rejects M prime, that must have meant that it couldn't have been sigma star, so it must have had prime lengths. Oh, but what do I know about M and W now? It couldn't have accepted W. So what should I say to my decider for ATM? I should say reject. Good. And then because of that, reg-len TM is undecided. Any questions about that? So what's the upshot? What we want of this machine when we do this, so reductions don't always have to be of the form, make this machine then run a supposed decider. Like here, I don't do that. But if you are going to do something like this, what you want to do is accept by default all the things you want to have so that they're not in the language. Okay? So I, by default, accepted the things that aren't in reg-len, that get me out of reg-len TM. Then, if M accepts W, I'll accept everything else. Or accept what I need to get to something that is in reg-len TM. Okay? Any questions about that? Any final questions at all? So, thank you for coming to my recitations. It's been fun.